Go. Good morning and welcome to this lecture. I think this is lecture number 10. What we were discussing in the previous class, previous lecture? Any idea?
We have completed nuclear fusion, sir.
We had completed nuclear physics. Yeah, I remember it. We have completed nuclear physics. And this is the time that we finished the remaining topics of modern physics. Did you get the new sheets that I had sent you?
Yes, sir. Electronic semiconductor.
Yes. So what we'll do in this lecture, lecture number 10, we will start with semiconductors. Again, this entire topic of semiconductor is a huge topic. I mean, there is a branch of physics specifically for this, electronics. Obviously, we are not going to discuss everything about it. What we are going to discuss is the basic things that we must know as students and those who are more likely to come in the exam. So we understand this, that we may not be doing the entire thing. I've already given you the notes. So you can go through the notes, and if you want, you can do a detailed study as well. What we'll concentrate on is the part which is more likely to come in the examination hall. Do we understand this? Yes or no, bacha?
Yes, sir.
So we will try to do that part that is more likely to come. So let us start. What is the first heading? I hope you have notes with you. Electronics, semiconductors. You know how the word electronic is derived? It is electron plus dynamics. So that becomes electronics, ICS. Doesn't matter if you don't know it or not. The field of science which deals with electron devices and their utilization is electronics. So basically we are into electronics. Again, it's basically a science branch, and what we got to do is you just need to understand the basics. Okay, we understand this. We can't do the entire topic. We'll just look at what we need to understand. The devices
Okay,
that
sir.
might be coming in the examination hall, rectifier. Do you know what is a rectifier? Do you know what is a rectifier?
No, sir.
Okay, amplifier, you might have heard. No?
Yes, sir.
Okay, amplifier, oscillator, all these are electronic devices. We will see what all devices we would require, and we will also see their uses. But first, let us start with this topic, which is known as energy band. Have you heard about this term, energy band? Energy band. Have you heard about this term, energy band? Okay, here I have a single silicon atom. We have n is equal to 1 shell, n is equal to 2 shell, n is equal to 3 shell. Do we understand this from chemistry? Different shells. N1,
Yes, sir.
principal quantum number n, 1, 2, 3.
Yes, sir.
Then they have this in terms of graph where the energy of these shells lie. Now, the last n is equal to 3 is known as the valence band. Do you know this? Do you know this? The last shell is the shell where you can add or remove electron, that is known as the valence band. Do we know this?
Yes, sir.
Now, above this valence band, we have shells which are empty. Do you see those shells that are empty? Do we see these shells above this valence band, the last shell? There are shells which are empty. Do we understand this?
Yes, sir.
Now, this is known as the conduction band CV. And as you can see, between the valence band and the conduction band, there is a energy difference of 1.1 electron volts. Do we understand this?
Yes, sir.
That is known as these are the different energy bands. Between first and the second, this is the difference. Between the second and the valence, this much is the difference. Between valence and conduction band, this much is the energy difference. Do we understand this?
Yes, sir.
This energy difference will be different for different atoms, for different elements. We understand this?
Yes, sir.
Now, that gives rise to this branch, which is known as electronics. Okay, because of this difference in energy band, we have this branch which is known as electronics. Now, we have seen the two bands, and I am going to show you this valence band VB. Do we see this valence band VB?
Yes, sir.
The range of energies possessed by valence electron is known as the valence band energy. Whatever energy those electrons have which are in the valence band are known as, the energy is known as valence band energy. Clear?
Clear, sir.
They have, you don't have to remember this. So basically you have to understand the last band is valence band. Remember, it's a very big topic and we have to cover it in very short. So I'll only give you the important points. Do you understand those points? You will mark those points, you will write those points, and you will just remember those points. Is it clear?
Clear, sir.
So only the highlighted part in valence band, rest is chemistry, we'll leave it to that. Then we have above valence band, we have the conduction band CV. What is the energy of this conduction band? Whenever you have a free electron in this band, whatever energy it has will be known as the conduction band energy. In general, it is partly filled by electrons. Remember, wherever we have an element, we don't have a single atom. We have a cluster. We have large number of atoms. So atoms from one, so electrons from one atom can move onto the valence or the conduction band of the second atom. Do we understand this? From the same element, from the same atom also, the electron can go to the conduction band. Remember, the electrons which are in the conduction band are very, very less. Do we understand this?
Yes, sir.
But there may be some electrons which are present in the conduction band. Do we understand this?
Yes, sir.
Normally, the conduction band, if it is empty, then conduction, electricity conduction is not possible, because conduction can only happen when you have free electrons. And free electrons, in which band are the electrons free? Tell me the answer. In which band are the electrons free? They are
Conduction
free
band.
only in the konsa band?
Conduction band.
Do we understand this, bacha?
Yes, sir.
Any doubts on this? Okay. Now,
Okay, sir.
we have valence band, electrons are present there. We have conduction band, maybe very few electrons are present there. Now, if an electron has to jump from valence band, which is lower shell, to conduction band, which is the higher shell, what we need to give it? Do we need to give it energy? Yes or no?
Yes, sir.
And we have already seen for silicon, how much is the energy difference? I told you to remember that, 1.1 electron volts. Do we remember this?
Yes, sir.
That is the energy that we are talking about, and you will mark this and note this. This is known as forbidden energy gap. Do we understand the meaning of forbidden energy gap? This is the difference between the conduction band and the valence band, and no free electrons can exist. Conduction band, as you can see, is higher up. Do you see this conduction band?
Yes, sir.
Do we see this valence band?
Yes, sir.
Electrons are present in the valence band. Very few electrons may be present in the conduction band. There is an energy difference between the two. This energy difference is known as the forbidden. God does not allow us to go into the conduction band. There is a forbidden zone. That forbidden zone is known as the forbidden energy gap. Do we understand this?
Yes, sir.
The width of this forbidden energy gap depends on the nature of substance. Now tell me, which substance will be a very good conductor? Apply some brain. Which type of element or which type of atom will be a good conductor? For a good conductor, what will be the value of the forbidden energy gap? Tell me, should it be very high or should it be very less? Should the width be very high or should the width be very less? If the width is very high, they will not be able to jump and it will not be a good conductor. Do we understand this?
Yes, sir.
If the width is more, the valence electrons are strongly attracted with the nucleus and they will not be able to jump into the conduction band, and therefore it may not be a good conductor. The width of the energy gap, forbidden energy gap, is given in EV. You must remember this. As temperature increases, a very important point, the forbidden energy gap decreases. Electrons get energy. They have now more energy. Therefore, they can easily jump from valence band to the conduction band, and therefore the width will decrease. Do we understand this? Please note this down. I'll give you a minute. Are we noting it down, bacha? Is everyone noting it down? Shall I move?
Yes, sir.
We have noted it down, sir.
Done, sir.
Okay, sir. Then, since we are talking about this energy gap, this diagram is going to show us how the energy gap is, how valence and conduction band are there in different type of substances. The first type is the conductor. Do you see the conductor?
Yes, sir.
The second type, which I will make in a different
Semiconductor.
color, is the semiconductor, which is the topic for our class. And the third type, I'll make it blue color. That is
Insulator.
my insulator. Now, looking at the diagram, I am not going to explain anything. Can anyone from you in the class tell me the difference between the three? Do you see the difference? Do you understand the difference? Yes or no? Do you understand the difference? What is
Yes, sir.
happening here? Yes. Explain what is happening in the conductor. What do you see in a conductor? In a conductor, what do you see, bacha? You see that the valence band, and the conduction band, valence band, and the conduction band are overlapping each other. Do you see this? They are overlapping each other. Do you see this?
Yes, sir.
They are overlapping each other. That means electrons can be present in the valence band as well as in the conduction band. A large number of electrons can be present in the conduction band because both the energy levels are overlapping each other, and therefore the electron can easily be present in the valence band as well as in the conduction band. As soon as the electrons are there in the conduction band, what will happen? We'll have good conductors. Do you understand this?
Yes, sir.
Moving on to the next category, which is semiconductor, which is the topic for this chapter. You can see that there is an energy difference of almost 1 to 1.5 to 1.3 electron volt. Valence band is lower, conduction band is upper. We will need at least approximately 1 electron volt of energy to make an electron jump from valence band to conduction band. We understand this?
Yes, sir.
But as you can see in the third case, the energy difference between the valence and conduction band in an insulator is very high, and therefore there are no electrons present in the conduction band, and therefore it becomes an insulator. बात समझ में आ रही है? Do we understand this?
हाँ sir, yes sir.
Yes, sir. Please, sir. Note it down, sir. They might give you a diagram and they might ask you which type of substance it is representing. If you see an overlap, that's a conductor. If you see 1 electron volt, that is a semiconductor. More than 3 electron volt, that becomes an insulator. Have you noted it down?
Done, sir.
Done, sir. Then, sir, this thing, sir, it is now written in words so that you can understand it. What happens in a conductor? In a conductor, conduction band and valence band are overlapping, so there is no band gap, no forbidden energy gap. The value of delta Eg, which is the gap, forbidden energy gap, is 0, due to which large number of electrons are available for conduction and therefore they become good conductors. You understand this?
Yes, sir.
Important point to note here is forbidden energy gap is 0. A large number of electrons are available for conduction in the conduction band. Such bodies are known as conductors. We understand conductors, yes or no?
Yes, sir.
Then we come on to the second category, which is the insulator. This color is not looking good. I will make it greener. The second category is the insulator. The energy levels are very high. Do we see this? Therefore, no electrons are available, and therefore it becomes an insulator. Do we understand this?
Yes, sir.
Please note it down, bacha. Have you noted it down, beta?
Completed, sir.
Completed, sir. But understand that in this chapter, we are not going to study conductors. In this chapter, we are not going to study insulators. What are we going to study in this chapter?
Semiconductors.
Semiconductor, and for semiconductors, the energy gap should be less than 3 electron volts. Normally, it's in the range of 1 to 1.5 electron volts, silicon or germanium, due to which electrons can be thermally excited. If you heat them up, it will go to the conduction band, and therefore the conductivity of the semiconductor lies between conductor, which are very conductive, and insulators, which are not conductive at all. Do we understand this? This is the topic for this chapter, semiconductors. Are we there in the same class, everyone? I'll give you a minute to note it down. Any doubts, please ask. Have you noted it down, bacha?
Done, sir.
Now, we are going to understand the properties of this semiconductor in detail. You will have to remember these properties, mark them, and note them. What are the examples of semiconductor materials? Most of the things that we are going to discuss here would be silicon and germanium. Do we understand this? But we have
Yes, sir.
inorganic semiconductors, organic semiconductors, and organic polymers as well, which can be treated as semiconductors. Which are semiconductors? You will have to remember their names. There could be a question that comes direct. Do we understand this? So this is just for you to remember. If you can remember it, it's good. What we have to understand here is the basic properties of a semiconductor, and the first property is negative temperature coefficient alpha. That means, oops, what I've done here. How do I get it back? Okay. Negative temperature coefficient alpha, that means the resistance. Oops, when I'm going here, it's getting colored everywhere. So I'll do it ulta. I will start from here. That is better. When you increase the temperature of a semiconductor, and which is a very special property of the semiconductor, when you increase the temperature, the energy band decreases, and therefore the resistance of semiconductor decreases, and conductivity of the semiconductor increases. Do we understand this?
Yes, sir.
Normally, in metals, when you heat them up, anybody, when you heat them up with temperature, the resistance should increase. But here in this case, the resistance is decreasing. Do we understand this?
Yes, sir.
They have a crystalline structure with a face center cube. Remember this? Conduction property may change by adding impurities, a very important thing. What are these impurities? We are going to see them, don't worry. We can change their conduction properties drastically by adding impurities. Do we understand this?
Yes,
They
sir.
are normally in the fourth group of your periodic table. Sorry. Again, the same thing has happened. Why is this happening? I don't understand. Okay. Energy gap is between 0.1 to 3 electron volts. Do we understand this?
Yes, sir.
Charge carrier are electron and holes. Again, the same thing. What is wrong? I don't understand. I will better not do this. I will underline this. Electron and hole. What is a hole? We will see that. Don't worry. Right now, just note them. You must know the electronic configuration of germanium, germanium 32, silicon 14. Do you know this? Yes or no? And you see that the valence band, or the number of electrons in the last shell, is 4. They are placed in the group 4 of the periodic table. Do we understand this?
Yes, sir.
Please note it down, sir. My
Okay,
health
sir.
is not good, sir, today, sir. Looks like, sir. So you will have to bear with me, sir. Just give me a minute, sir. Note it down, sir. So, sir, we have noted it down, sir.
Yes, sir. Done, sir.
Done, sir. Then, sir, this diagram, sir, you don't have to draw this diagram. You just have to understand it. Do we see that the difference in energy between the valence and the conduction band for germanium is only 0.7 electron volt? Do we see this?
Yes, sir.
But for silicon, the same thing is 1.1 electron volt. So, which you think is a better semiconductor based on this observation?
0.7 electron volt.
That is germanium. Do we understand this?
Yes, sir.
When you have 0 Kelvin, at 0 Kelvin, semiconductors have no conductivity. 0 Kelvin is impossible to achieve. At any other temperature, some electrons will jump to the conduction band and therefore they will behave as conductors, but they will behave as poor conductors. Do we understand this?
Yes, sir.
Do we understand this, bacha?
Yes, sir.
There will be some electrons which are present in the conduction band, but those will be very, very less, and hence the conduction would be very poor. As you can see, they have shown two structures, silicon at 0 Kelvin, valence band is fully filled, conduction band is fully empty. Do we understand this? Zero conductivity. It does not behave as a conductor. But what we have here, at any other temperature, you see something as a hole. What is a hole? You'll understand this, don't worry. At any higher temperature, valence band would be partly empty and the conduction band would be partly filled because some covalent bonds are going to get broken and these electrons will become free and they will jump into the conduction band. We understand this principle, bacha?
Yes, sir.
We'll move ahead. I hope you have understood this.
Understood, sir.
Okay. Now, since we have uttered this word whole many times, now is the time that we understand the meaning of this term whole. Again, remember, bacha, I'm only going to discuss that part which is going to come in the exam because this is a very vast topic. Even if I try my very best, I cannot cover it in 2 or 3 classes and I have to finish it in 2 or 3 classes. We understand this, yes?
Yes, sir.
Now, this is a hole. We have already shown you the hole in the previous diagram. This is a bigger version of this diagram. I guess you can't see that entire thing. So what I'm going to do is I'm going to make it smaller. Can you see it bigger now on the screen? I don't have my screen, so I don't see what you see. Do you see this diagram
Yes,
bigger?
sir. Yes, sir.
Can you see this small thing hole? It's pointing to somewhere here. Do we see this?
Yes, sir.
Okay. You don't have to draw the diagram. You just have to understand it. I have just shown you the bigger picture that this is a hole. Now, what is a hole? Looking at the picture, can you tell me what is a hole? Just looking at the picture. The picture that I'm showing you right now. Obviously, it's not RRR. It's better than RRR, right? Yes or no? Or RRR is better. This picture is better or RRR?
RRR.
RRR. Okay. Chalo. What is a hole then? Due to external energy, temperature, radiation, electron will jump from the valence band to conduction band. Do we understand this?
Free electrons.
If I heat up this semiconductor, any metal, particularly semiconductors we are talking here, some electrons will jump from valence band to conduction band? Yes or no?
Yes, sir.
Because of this, there will be a vacancy. One electron, let us say, has jumped from valence band to the conduction band. So there is a deficiency or vacancy of one electron. Yes or no?
Yes, sir.
One electron is less. We can say it in a different way that one positive charge is more. Yes or no?
Yes, sir.
One negative charge less is equal to one positive charge more. Yes or no?
Yes, sir.
This electron vacancy is known as hole. So if there is a vacancy of electron, how this vacancy is created? Electron jumping from valence band to conduction band, you have a vacancy, deficiency of an electron. That deficiency is known as a hole. We understand this?
Yes, sir.
What type of charge will this hole have? Now, this hole does not have its independent existence. We are calling deficiency of electron as a hole. Hole does not exist. We are calling the deficiency of electron as a hole. What type of charge will this hole have? Positive or negative?
Positive.
Yes, sir. So positive charge is hole. As we understand this.
Yes, sir.
Property of hole. It is missing electron. We understand this. It acts as a positive charge. We understand this.
Yes, sir.
Its effective mass is more than electron. Remember this. Mobility is less than this. It is a virtual charge. There is no physical charge. We understand this.
Yes, sir.
That are the properties of hole, and then we have hole current. What is hole current? Same thing. When you heat something up, covalent bonds are broken. Electron will jump into the conduction band. If you apply electric field, these electrons will move. That current is known as hole current. Do we understand this?
Yes, sir.
1 minute. Please note it down.
Okay, sir.
You have to note down the properties of hole and what is hole current. Have you noted this on, bacha?
Done, sir.
Okay. So, what we have seen up till now is silicon or germanium, which are just semiconductors. How many electrons they have in the outermost shell? Tell me, fatafat. How many electrons they have in the outermost shell? We don't know how many electrons silicon and germanium has in the outermost shell.
4.
Come on, you should not take so much time. 4. Some of these electrons in the valence band will move into the conduction band, but the conductivity will be very less. They will not be good conductors. Yes or no?
Yes, sir.
How can I make this silicon and germanium more conductive? That is the question. Because in their original state, we call it pure silicon or pure germanium. Pure silicon ka crystal या pure germanium ka crystal, block, whatever you call it. If it consists of pure silicon and germanium, the conductivity is going to be very less. We understand this. The conductivity would be very less. Do we understand this?
Yes, sir.
The question is, how can we increase the conductivity of the semiconductors? And the answer is, they are
By increasing
pure.
temperature.
They are pure, you make them impure. What do you understand by making them impure? We add
Without impurities.
pure silicon, pure germanium, they are not good conductors. I want to make them better conductors, so I'm going to add something inside them. That something is going to make them better conductors, and that something is known as impurity. Do we understand this?
Yes, sir.
When we insert this impurity, these semiconductors, silicon and pure germanium will become better conductors. Do we understand this?
Yes, sir.
Please note it down, sir.
Done, sir.
Done, sir. Then, sir, when I put this impurity inside this silicon or germanium, that process is known as doping. You might have heard this word doping. Yes or no?
Doping.
Doping, when someone takes a illegal drug in sports,
Yes,
we
sir.
call it doping. Here, doping is different, bacha. Here, doping is again taking impurity inside a pure sample. That is
Cannabinoid.
doping. Do we understand this? Yes or no? Do you understand this? Do you understand this term doping?
Yes, sir.
The dopant element ka concentration should be very low. Remember this. Doping ratio should be very low. 1:10 raised to the power 6 to 1
10
is
to the
to
power
10 raised to the power 10. Do we understand this? For 10
Yes,
raised to
sir.
the power 10 atoms, you add just one of this doper or dopant. Do we understand this?
Yes, sir.
There are two methods of doping. One is on the alloy method, one is on the diffusion method. This is the best. I know nothing about them. You also know nothing about them. You just have to remember this. Do you understand this?
Yes, sir.
The size of the dopant should be same as that of crystal. Otherwise, the structure will become good. We need to maintain the crystalline structure of the pure silicon or pure germanium. So if I put something which is of different size, the structure will become distorted. Yes or no?
Yes, sir.
So we add impurity or dopant of the same size. Remember, these are the properties of this dopant. Should not forget it. Will you remember it, bacha?
Yes, sir.
Yes, sir. Please note it down, sir.
Done, sir.
Okay. Just give me a minute, sir. Okay, sir. Now, sir, this, sir. Two types of semiconductors we will encounter. The first is the intrinsic or the pure semiconductor. Pure semiconductors are known as intrinsic semiconductors. Do we understand this? This is pure silicon or germanium. We understand this? Please raise your hands.
Yes, sir.
You understand this? Do we understand this?
Yes, sir.
Then we have the doped semiconductor, the impure semiconductor. We call it extrinsic semiconductor. Now, this extrinsic semiconductor can be of two types. It could be of N type, negative type. It could be of P type, positive type. For negative type or N type, what do? We add a pentavalent impurity. Pentavalent means it has 5 electrons in the outermost shell. Do we understand this?
Yes, sir.
Phosphorus is the name that you must remember. Phosphorus is what we add normally. For a P type, positive type, we add a trivalent impurity, an atom which has 3 electrons in the outermost shell, gallium, boron, aluminum, and all that. We can add that atom. N type are also known as donor because they have 1 extra electron, so they can give donor, 1 electron extra, negative. So N, pentavalent, 1 electron extra, negative. Do we understand this?
Yes, sir.
For trivalent impurity, I have 3 electron, I have 1 electron less. So I will accept electrons. Give. I accept electrons. I take electrons from there. Therefore, it becomes positively charged. We understand this?
Yes, sir.
Please note it down, sir. Important point, sir.
Okay, sir.
Have you noted it down, sir?
Completed, sir.
Completed, sir. Then, sir, more description, sir. N-type semiconductor. I will add a pentavalent impurity. It has 5 valence electrons. 5th electron is set free. So 1 electron extra. Do we understand this? Because of 1 electron extra, it will be known as N-type. Do we understand this?
Yes, sir.
Here, this free electron, and we'll have a lot of free electrons. These are majority carriers because they are more, so they will carry more current. Do we understand this?
Yes, sir.
But at the same time, there will also be holes. Holes are created when electrons jump from valence band to conduction band. Do we remember this? Yes or no?
Yes, sir.
These holes will be present, but they will be only present in very less amount, and those will be minority carriers. Do we understand this? N-type semiconductor, pentavalent impurity, 5. Do we understand this?
Understood, sir.
1 minute, 2 minutes. Please note it down.
All right.
Have you noted it down, bacha? Are
Done.
are we there in
Done,
the
sir.
class? Everyone has slept.
Sir, done, sir. Done, sir.
You are there?
Yes, sir.
Yes, sir. This was about N type. Now, if you have understood N type, you do the reverse of it and you will get P type. So, what will happen in P type?
Okay.
I will dope it with a trivalent impurity.
Electron acceptor.
One electron is less. One electron is
One-
less. Do we understand this?
Yes, sir.
So,
Yes, sir.
this is known as the acceptor impurity. It will accept, hey, give me, give me, give me. If it accepts electron, one electron is less. So, one hole would be created. Yes or no?
Yes, sir.
Free electrons are very less. They are there, but they are very less. They are minority carriers. And hole become majority carriers. Do we understand this?
Yes, sir.
Please note it down. A minute, 2 minutes.
Mata, mata. Done, sir.
Have you
Done,
noted it down,
sir.
bacha?
Yes, sir. Completed.
Now, we'll make a table. In that table, we will be dealing with all the three together. All the three means the first is intrinsic semiconductor. Do we understand what is intrinsic semiconductor?
Yes, sir. Pure conductor.
What?
Pure conductor.
Pure, yes, pure ghee, pure semiconductor. Then we have N type, the pentavalent, and then we have P type, the trivalent.
Acceptor.
Yes, here we have difference in energy level. Here we have difference in energy level. Here we have difference in energy level. What has changed here? That I put a donor impurity. The donor impurity level is higher up, and the acceptor level impurity is low down. So that is what you should remember. Do we understand this? Donor
Sir.
impurity, the band level is higher and acceptor is lower. Will you remember this?
Yes, sir.
Yes, sir, no, sir.
Sir, yes, sir.
Now, in intrinsic semiconductor, current is due to electron as well as hole. In N type, it is majorly due to electron. They are the major carriers. Do we remember this?
Sir, yes,
In
sir.
P type, the current is due to
Holes.
hole. Point number 4, number of electrons and number of holes are same. Here number of holes is very, very less. Here number of hole is very, very high. Here the total current is hole current plus electron current. Here total current is almost equal to electron current. Hole current is very less. Here the total current is almost equal to hole current. Electron current is very less. Do we understand this? Yes or no? Please tell me.
Yes, sir.
Please note it down, sir.
Completed, sir.
Have you noted it down, bacha?
Completed, sir.
Then the remaining points again. The entire thing is just based on this. In N type, electrons are the majority carriers, holes are the minority carriers. In P type, holes are the majority carriers and electrons are minority carriers. Remember, all these three are entirely neutral. They don't have any charge of their own. Quantity of electrons and holes are equal. Everything just boils down to the same thing, that in N type, electrons are more and holes are less. Do we understand this? Please note it down. Have you noted down, bacha?
Yes, sir.
Okay. Then we'll go through this small thing that you must remember. This is known as the mass action law. Just write the heading mass action law. And then what do? Write the heading mass action law. We are not going to discuss this any further, and we'll just write the formula that we have for this mass action law, and the formula is here that I'm going to show you. And this is the formula that you have to remember by the mass action law. Under thermal equilibrium, the concentration of free electron and the concentration of hole Ne and NH, if you take the product, that is a constant. Ne into NH is equal to Ni square, which is a constant. Just remember this. Do we understand this? This is the only thing that you have to remember in the entire law. You might get a question straight away from this chapter, from this topic. Please remember this. Have you noted it down, bacha? Have you noted it down, bacha?
Yes, sir.
Okay, then let's move ahead and we'll move quickly to this topic. Resistivity and conductivity of a semiconductor. How do we calculate the resistivity and the conductivity? Before going on to semiconductor, let us have a look at what is conductivity of a semiconductor. You must be knowing this equation for the conductor. Drift velocity is mu, which is mobility multiplied by E. Yes or no?
Yes, sir.
Conductivity sigma is 1 by rho, where rho is the resistivity. Yes or no?
Yes, sir.
J, which is the current density, is sigma multiplied by E, which is Ne into mu into E. You have to remember all these formulae. Do we remember these formulae? Yes or no? Bacha, do we remember these formulae?
Yes, sir.
Please note them down once again, sir. Formula for current NAEVD, formula for current density I by A, formula for drift velocity, formula for mobility, formula for J is equal to sigma E, which is your Ohm's law. Please note them down once again so that you can keep them together. So that you can keep them together. Do we understand it, bacha? Have we written this? Have you done this, bacha?
Done, sir.
Then we come to, in semiconductors, the formula are same. In intrinsic semiconductor, number of holes and electrons are same. Yes or no?
Yes, sir.
Current density is NE into VD. Here we have two drift velocity of electron and drift velocity of hole. Do we understand this?
Yes, sir.
Conductivity is 1 by rho. So En into concentration or mobility of electron plus mobility of hole. Do we understand this?
Yes, sir.
Here in P type, number of holes is very more. So we have N H into VH into E. Do we understand this? Only holes wale terms are coming. Do we understand?
Yes, sir.
Here it will be simply equal to multiplied by the mobility of the holes. Here we have mobility of the electron. Do we understand the difference in the three?
Yes, sir.
Yes or no?
Yes,
In
sir.
in N type only electron wale term will come. In P type only holes wale term will come. In intrinsic both electron and holes wale term will be there. Do we understand this?
Yes, sir.
Please note it down, sir. Are we ready to solve some questions, sir?
Yes, sir.
This one, sir, is the first one, sir. Best of luck, sir. Again, this is taken from your sheet. Then look at the sheet. The question is, what will be the conductance of pure silicon crystal at 300 Kelvin? Electron hole pairs per centimeter is 1.072 into 10 raised to the power 10. Mobility of N, which I think is H. There must be a printing mistake, so you can take it as uh, mobility of electron as this and mobility of hole like this, or proton, whatever you call it. Will you have to solve this? Yes or no?
Yes, sir.
I'll give you a minute, sir. Put the formula and get the answer, sir. Did you get the answer, beta? Well, how to do it? It's very simple. I have to put the formula for conductivity. Do we remember this formula for conductivity?
Yes, sir.
Concentration of electrons into charge of the electron multiplied by the mobility of electron. Do we remember this? Concentration of hole multiplied by charge multiplied by mobility. Do we understand this?
Yes, sir.
Here both the concentrations are same. Concentration is given as 1.072 into 10 raised to the power 10. Charge of an electron is 1.6 into 10 raised to the power minus 16. Yes or no?
Yes, sir.
We just add the two mobilities. One mobility is given as 1350. The other mobility is given as 480. We just add this and multiply and we will get the answer. Do we understand this?
Yes, sir.
Do we understand this? Do we understand this?
Yes, sir.
Okay, sir. Please note it down, sir. Then I'll give you the next question, sir. These questions I have seen coming in the examination hall in the paper, and that is why we are doing it. We'll do 3 questions. That was the first one based on conductivity. Then the second one will come. Are we ready for the second question?
Yes, sir. Yes, sir.
Yes, sir. Then, sir, this one, sir. The next question in the exercise in your sheet. Pure silicon at 200 Kelvin has equal electron and equal hole concentration. The value is given. Doping by indium increases hole का concentration to 4.5 into 10 raised to the power 22 per meter cube. What is the concentration of electron in doped silicon? Very good question. Very simple one. If you know the formula, you can do it. I'll give you a minute to do it. Anyone could solve this question, bacha? No one? Shall I give you a hint? In the beginning, both were having
Achin. 5 into 10 to the power of 9.
5 into 10 to the power 9. That is exactly the answer. And how have we done it? It is very simple. Yes or no?
Sir.
The product of Ne and NH are always constant. In the beginning, it both were 1.5. 1.5 into 10 raised to the power 16. So I multiplied them twice. 1.5 into 10 raised to the power 16 whole square. Do we understand this? That will come Ni
Yes,
square. Ni square. The formula is Ni square is equal to Ne multiplied by NH. Do we remember this? Do we understand this?
sir.
Do we understand this, bacha? Yes or no?
Sir.
Ni is 1.5 into 10 raised to the power 16, the original concentration. That should be equal to Ne, new concentration of electron, multiplied by NH, new concentration of hole. We know the new concentration of holes. From there, you can calculate the new concentration of the electrons. Yes or no?
Yes, sir.
Yes, sir?
Yes, sir.
Okay, sir. One more question, the last question, and then we will call this class off. If you can do this, well, I would be very happy that we have understood what we have discussed in the class today. Here comes the question, and you have a minute to win it. A semiconductor has equal electron and hole concentration that is given. On doping with a certain impurity, the electron concentration increases to this. The first question is very simple. Identify the new semiconductor. Will it be p-type or n-type? Tell me, p-type or n-type?
N-type.
Yes?
N-type, sir.
N-type, sir. You have to find the new hole concentration, sir. Do I have the answer for the new hole concentration?
Ne is greater than Ni.
Can I have the second answer, please?
Into 10 to the power of 4.
Yes?
4 into 10 to the power of 4.
4 into 10 to the power 4. That is exactly correct. Ni squared is 6 into 10 raised to the power 8 ka squared. Ne we already know. From there you can find the whole concentration. Yes or no?
Yes, sir.
Everyone got this? Can I have some reason that we understand this? We got this? Yes, bacha. Well done. Okay. So we are done with this whole concentration, electron concentration, p-type and n-type. In the next class, we'll go on. And if I can give you some things that we are going to do in the next class, we will be doing p-n junction. What would be p-n junction? It's very simple. You will have a p-type semiconductor, you will have an n-type semiconductor, and you are going to join them. That becomes a p-n junction. Do we understand this?
Yes, sir.
So we'll be dealing with this p-n junction in the next class. I hope you love this class. Go through the notes on p-n junction. There are some more problems in the sheet. If you can do them, very good. I'll wind up today's class here. The next class, I'll see you. Take care. Have a nice day, beta.
Take care, sir.